A strong acid is an acid that ionizes 100% in solution. For example, hydrochloric acid, HCl, is a strong acid. It donates a proton to water, H₂O, to form the hydronium ion H₃O+, and the conjugate base to HCl, which is the chloride anion Cl-. In reality, this reaction reaches an equilibrium. However, the equilibrium lies so far to the right and favors the product so much that we don't draw an equilibrium arrow. We simply draw an arrow going to the right, indicating the reaction essentially goes to completion. And if the reaction essentially goes to completion, we can say that hydrochloric acid ionizes 100% and forms hydronium ions and chloride anions. So essentially there's no more HCl left. It's all turned into H₃O+ and Cl-. It's also acceptable to completely leave water out of the equation and to show hydrochloric acid HCl turning into H+ and Cl-. Once again, since HCl is a strong acid, there's only an arrow going to the right, indicating HCl ionizes 100%. And since there's only one water molecule difference between H+ and H₃O+, H+ and H₃O+ are used interchangeably. Hydrochloric acid is an example of a monoprotic strong acid. Monoprotic means hydrochloric acid has one proton that it can donate in solution. Other examples of monoprotic strong acids include hydrobromic acid, HBr, hydroiodic acid, HI, nitric acid, HNO₃, and perchloric acid, HClO₄. Sulfuric acid is H₂SO₄, and it's a strong acid, but it's a diprotic acid, meaning it has two protons that it can donate. However, only the first ionization for sulfuric acid is strong. Let's calculate the pH of a strong acid solution. In this case, we're going to do a 0.040 molar solution of nitric acid. Nitric acid is HNO₃, and nitric acid reacts with water to form hydronium H₃O+ and nitrate NO3-, which is the conjugate base to HNO₃. Because nitric acid is a strong acid, we assume the reaction goes to completion. Therefore, if the initial concentration of nitric acid is 0.040 molar, looking at our mole ratios in the balanced equation, there's a 1 in front of nitric acid, and there's also a 1 in front of hydronium and a 1 in front of nitrate. Therefore, if the reaction goes to completion, the concentration of hydronium would also be 0.040 molar, and the same with the nitrate anion. That would also have a concentration of 0.040 molar. Since our goal is to calculate the pH of this solution, we know that the equation for pH is equal to the negative log of the concentration of hydronium ions. Therefore, we just need to plug in the concentration of hydronium ions into our equation. This gives us the pH is equal to the negative log of 0.040, which is equal to 1.40. So even though this is a pretty dilute solution of nitric acid, because nitric acid is a strong acid, the pH is pretty low. Also note, since we have two significant figures for the concentration of hydronium ions, we need 2 decimal places for our final answer. Let's do another problem with a strong acid solution. Let's say we have 100 milliliters of an aqueous solution of hydroiodic acid, and the pH of the solution is equal to 1.50. And our goal is to find the mass of HI that's present in solution. Hydroiodic acid reacts with water to form the hydronium ion and the iodide anion, and the mole ratio of HI to H₃O+ is 1 to 1. So if we can find the concentration of hydronium ion in solution, that should also be the initial concentration of hydroiodic acid. And once we find the initial concentration of hydroiodic acid, we can find the mass of HI that's present. Since we're given the pH in the problem, we can plug that directly into our equation, which gives us 1.50 is equal to the negative log of the concentration of hydronium ions. To solve for the concentration of hydronium ions, we can first move the negative sign to the left side, which gives us negative 1.50 is equal to the log of the concentration of hydronium ions. And to get rid of the log, we can take 10 to both sides. So the concentration of hydronium ions is equal to 10 to the negative 1.50. which is equal to 0.032. So the concentration of hydronium ions is 0.032 molar. And because the mole ratio of hydronium ion to Hi is 1 to 1, the initial concentration of Hi is also 0.032 molar. Now that we know the initial concentration of Hi, we're ready to find the mass of Hi present. Molarity is moles per liter, so let's go ahead and rewrite this as 0.032 moles per liter. The volume of the solution is 100 milliliters, which is equal to 0.100 liters. So if we multiply moles per liter by the volume, which is 0.100 liters, liters will cancel and give us moles. So this is equal to 0.0032 moles of Hi. Since our goal is to find the mass of Hi present, the final step is to multiply the moles of Hi by the molar mass, which is 128 grams per 1 mole of Hi. So moles of Hi would cancel out, and this gives us 0.41 grams as our final answer.